Well, it's a great pleasure to have Luca here today, and he's going to talk about the dynamic of near extremal and near-BPS black holes.
Thank you so much for the invitation. It's a pleasure to be here. I'll be here for the rest of the afternoon and tomorrow. So if you guys have questions about the talk or anything else, please feel free to reach out. As Chris said, I'll be talking about the statistical mechanics of near-extremal and near-BPS black holes. This is work done in collaboration with a bunch of people that I'll reference throughout the talk. First, I'll want to explain an old puzzle that has existed about the thermodynamics or statistical mechanics of near-extremal black holes for a couple of decades now. So the old puzzle that exists is the following. So suppose that I look at black holes semi-classically, and by that I mean that I take their solutions and I plug that solution into, let's say, the Einstein-Maxwell action. So I consider black holes coupled to electromagnetism. Such black holes could have a variety of temperatures and could be as big as I want. When black holes have zero temperature but non-zero mass, so they could be macroscopic black holes but still have very low temperature, they're called extremal. So here I'm going to plot what happens to the mass of the black hole as I raise the temperature above extremality. So a simple calculation shows that extremal black holes, at least semi-classically, have no linear in temperature term in their mass. So this is their mass above extremality, and they behave like t squared. And I'll explain what the meaning of the coefficient of t squared is in a second. Okay, so these gentlemen observed this phenomenon, and this just alone brings a puzzle. And the puzzle is the following. So consider a single Hawking quanta. We all know that black holes emit radiation when they're at finite temperature. So why don't we consider a single Hawking quanta? Well, a simple calculation shows you that the average energy of a single Hawking quanta is proportional to the temperature of that emitted quantum. So it means that even for a single Hawking quantum, there's a regime in which the average energy of a photon could be larger than the energy that a black hole has above extremality. So for instance, if I had a black hole at this temperature, let's say here, and I radiated a single Hawking quantum that would have this energy, then the temperature of the black hole would change drastically by an order 1 amount. So let's say T before and T after over T before could be something arbitrarily small. So, and something even worse happens if the black hole is within this range. In that case, it almost seems like I cannot radiate quanta to begin with. So this automatically, the fact that I cannot radiate even a single quantum of radiation can be associated to a breakdown of black hole thermodynamics. Because in thermodynamics, we assume that we can exchange an infinite number of degrees of freedom until we reach thermal equilibrium with, let's say, a bath system. And that assumption just doesn't hold here. So these gentlemen viewed this as a breakdown of semi-classical thermodynamics that somehow needs to be resolved. So the breakdown occurs at an energy E gap, which is where these two plots intersect, which is the energy that multiplies this factor of t squared in the energy that black holes have above extremality. And by the way, this is a very general plot. It applies to extremal Kerr black holes, extremal Breinster-Nordstrom. Take your favorite extremal black hole, raise its temperature a little bit, and you'll see that it goes like t squared instead of going linearly with t. Good. So another way, before I go there, just to give you a concrete example of what that energy scale where the two plots intersect actually is. If we take Breinster-Nordstrom black holes in our own universe, so let's say we take them in 4 dimension in flat space, then the coefficient of t squared is just given by the Planck length multiplied by the charge of the black hole raised to the cubic power. So in some sense, you could see this as some power of the entropy that's given energy units by g Newton. So a different way of phrasing the same problem is the following. I don't know what happens to black holes at extremely low temperatures, which means equivalently, I don't know what happens to the density of states of black holes close to extremality. So I'm interested in what happens as the energy of that black holes have above extremality reaches the scale that I called in the previous plot E gap. And I'll tell you why it was called E gap in a second. So semi-classically, I could perhaps trust this plot of the density of states of black holes in this region that's very far from this scale E gap. But perhaps I expect there to be corrections that drastically affect the density of states in between extremality, which here is at 0, and the scale E gap. So the question is, how does this plot get corrected at small energies? So one proposal came from string theory in the 90s by Maldacena and Susskind in the D1, D5 theory. They have a D-brane construction in which, by extrapolating from weak coupling, so that's an assumption, they kind of explained that such black holes have a gap. So the energy scale E gap that at which those two plots intersected should be literally understood as a gap in the spectrum of black holes. So that means that they claim that string theory tells you that there are no black holes within this energy range. There is some degeneracy at extremality, after which there is a gap in energies, and maybe there is some dense spectrum of black hole microstates starting at this energy gap. This was further supported by some computations that Maldacena and Strominger did in two-dimensional conformal field theories, which kind of painted the picture that this gap should be a more general phenomenon that applies even beyond the D1, D5 system, which is a particular string theory setup. So one thing that all these setups have in common, though, is that the theory that they start with and the black holes that they analyze are excitations above a black hole that preserves some supersymmetry. So these are called BPS black holes. So asking whether or not there is a gap is important. We want to understand whether this gap is an artifact of supersymmetry, or is it more generic, and does it apply to the black holes in our own universe, where we might not necessarily excite an extremal supersymmetric black hole. We might excite a black hole that doesn't preserve supersymmetry. So we want to ask, does this apply to Reinstein-Nordstrom and Kerr-Newman black holes in our own universe? Oh, sorry. We should also ask whether the same conclusions hold for black holes not in the D1, D5 system, but in other setups. So famously, in string theory, there's this concept called AdS5 where black holes and the bulk can be mapped to CFT states on the boundary side, heavy CFT states. So the question of whether or not there is a gap in the bulk maps to whether or not there is a gap between certain CFT states on the boundary side. A related question, and this is the final open question that I'll mention, is whether e to the S0, where S0 is the extremal entropy, should be really understood as a ground state degeneracy, especially in the non-supersymmetric case. So as you all know, the entropy of the black hole is proportional to its area, measured in Planck units. So in the absence of supersymmetry, what protects this exact degeneracy that the classical computation seems to exhibit. So just to show you how massive this degeneracy can be, this is just maybe a naive example, but suppose I take a Reister-Nordstrom black hole in our own universe with the mass of a sun, then the classical computation predicts that e to the S0 is 10 to the 10 to the power 76, which would be an absolutely crazy degeneracy to talk about in the absence of any symmetry. So the question is this e to the S0 really a degeneracy, or is it something else? More concretely, there's been a really great effort in the past couple of decades to compute corrections to the black hole entropy. Quantum corrections, let's say, for instance, Astronomy famously has computed logarithmic corrections to the black hole entropy. But none of those logarithmic corrections seem to say that this huge degeneracy disappears in the absence of supersymmetry. So are there corrections that really address the presence or absence of this degeneracy? And to make the problem even more concrete, we know that in the presence of supersymmetry, there are string theory examples in which the degeneracy of black holes has been counted exactly. This is what Strominger and Waffe have did. So they counted some states in string theory, which in the strongly coupled limit are associated to a black hole degeneracy, and they get an exact integer. So they can count it exactly. However, in these theories, one could take a theory that's supersymmetric and a theory that's not supersymmetric, but has the same bosonic sector, let's say. So what type of corrections distinguishes these two theories? How come there can be a huge degeneracy in one case and the absence of a degeneracy in the other case? So to take an unbiased view, since all the computations that I previously mentioned relied on string theory, I will not call the energy scale in which the two plots intersected in the first slide, I won't call that E gap. I'll call that ESL2, and I'll explain why in a second. And when I talk about S0, I won't refer to it as the log of the extremal degeneracy. I'll still call it extremal entropy, but in the back of your minds, I want you to not necessarily imagine the typical connection in StatMech between degeneracy and entropy. So the concrete computation that we'll be doing is that we'll compute the partition function and density of states of near extremal black holes in a low temperature expansion. The theory in which we'll be doing it is we'll be doing it in Einstein-Maxwell theory first to see what happens with non-supersymmetric black holes. And then we will be doing it in 5D n=2 minimal gauge supergravity in AdS5. This is a theory that's widely considered in string theory because completion of it is dual to a famous quantum field theory, which is called n=4 super YangMills, which has been very widely studied. And the idea here is that we'll try to understand the effective field theory that describes the relevant degrees of freedom in the near horizon region at very low temperatures. And this is where a theory that has been widely considered in the past couple of years, and long before that, but it kind of had a resurgence in the past couple of years. The theory is called JT gravity, and we'll see that it describes the relevant degrees of freedom that capture the temperature dependence of the partition function. And there's a huge number of papers, I couldn't actually list all of them, that talk about the connection between near extremal black holes and JT gravity. The most papers address this question, this relationship at a classical level. I think what we do slightly, I think what we do slightly differently is that we try to understand how the quantum corrections in JT gravity are related to quantum corrections obtained from fluctuations of the metric in actual black holes. Okay, so any questions? Let me lock the screen so that it doesn't rotate. Okay, there's no questions. I'll go forward. So let me start with the partition function of Reister-Nordstrom black holes in Einstein-Maxwell theory. So Einstein-Maxwell theory, as I'm sure you all know, is a theory of that contains a metric, an Einstein-Hilbert term with a possible cosmological constant. Here, I'll mostly be talking about black holes in AdS5, just to make the comparison between the non-supersymmetric and supersymmetric black holes more concrete. Although all the conclusions that I'll mention here applies to all near-extremal black holes and non-supersymmetric theories across a variety of space-time dimensions. So in addition to the Einstein-Hilbert term, there's a Maxwell term, and such a theory has black hole solutions that are either electrically or magnetically charged. And those black holes can be however big, but have a temperature however small. Instead of trying to understand the theory in 5 dimensions or 4 dimensions, I will consider an ansatz for the metric, which is consistent with the symmetries of such black holes, in which I separate the metric into a 2D metric that has a size that's parametrized by R0 divided by some scalar field, chi, that's called a dilaton, where this chi parameterizes the area of the transverse space. So in 4 dimensions, this chi parameterizes the size of the sphere as I go away from the horizon. In 5 dimensions, in AdS5, it parameterizes the size of the S3 as I go away from the horizon. So what happens if I take this ansatz and plug it into the 5D action? I get the following theory. I get a 2-dimensional theory that has a metric that appears for the Ricci scalar and square root of g that's coupled to the dilaton field chi that I mentioned previously. The reason why I parameterize the 5D or 4D metric in this way with a factor of 1 over chi to the 1/2 in front of g mu nu is that if one parameterizes the metric in this way, it's a general ansatz. But the nice thing about it is that it ends up having no kinetic terms for the field chi. So the field chi is non-dynamical if I plug it into the metric. Okay, so I plug it in, I obtain a coupling between the dilaton and the metric. This is just the theory of 2D dilaton gravity that has some potential u of chi. It's coupled to an SO free gauge field that captures the isometries of the internal space. In this case, the internal space is S free if I'm in 5 dimensions. So this is like a YangMills term coupled to the dilaton chi. There is a term that comes from dimensionally reducing the Maxwell field that existed in 4 or 5 dimensions. And finally, there is an entire tower of massive Kaluza-Klein modes. So these are just excitations of all the fields that are not captured by these 4 fields: the dilaton, the metric, the 2D metric, the SO4 gauge field, or the Maxwell field. But the important thing is that they're all massive. And the nice thing is that one can show that if you can integrate out these KK modes, they don't actually affect the temperature dependence of the partition function. So I won't go into too much detail about this. I'll just mention it how these KK modes will come up in a few slides. But essentially, we can consider the theory without this entire tower of KK modes. Yeah. So it parameterizes the diffeomorphisms on S3, the possible rotations on S3.
We're starting in 5 dimensions and reduce it down.
Exactly. We start in 5 dimensions and reduce it down to 2D. And when you do that, there is a gauge field that captures the isometry of the internal space. So if this was if we were in 4 dimensions, this would be an SU2 gauge field. And if we're in 5 dimensions, this is an SO5 gauge field. So this is just the action that appears from this reduction.
But is this a consistent
No, it's not a consistent truncation, but the point is that if you integrate out these KK modes, they don't generate a temperature-dependent factor in the partition function. So these are the degrees of freedom that actually affect the temperature dependence of the partition function at leading order, which is what we're interested in, because we're interested in the density of states at low energies. Okay. So one can actually solve this, since this is like a 2D problem. It's actually very easy to solve for what chi is and what g is by solving the equations of motion. And not surprisingly, what one finds if one fixes the field strength of the SO4 gauge fields to 0, this fixes the angular momenta around S3 to be 0. And if one fixes the charge of the black hole Q by fixing the field strength of the 2DU1 gauge field, then one finds precisely the Reinster-Nordström solution that all of you know that was discovered 100 years ago. So this is just a very simple way, since I just, my ansatz for the metric is consistent with the symmetries of Reinster-Nordström. And if I turn on small j, so there's a J1 and a J2, but if I turn on my field strength, my SO4 field strength to be a bit non-zero, then what I find is not Reinster-Nordström solutions, I find Per-Newman solutions. Those are solutions that hold both electric charge or magnetic charge, but also a bit of angular momentum. Good.
Why do you need to keep J small?
Yeah, so what happens is that for larger J, other fields get a large VEV. So the way in which I made the assumptions is inconsistent. I should have kept some of the KK modes of other fields.
So this for 5 dimensions, right?
Yeah. So here it's J1 equal J2 equals 0. Yeah. So from now on, in this example, we will study the canonical ensemble with J equals 0 and macrocanonical for Q. This is just to keep things simple and not have like a bunch of parameters lying around. The point, though, is that I could work at non-zero J as long as it's small and I don't turn on those KK fields that I was mentioning about earlier. So good. So what I want to do with the solution now is I'm interested in the behavior of such black holes at low energies, which is equivalent to asking what the density of states is from the partition function when computed at low temperature or at inverse temperature much larger than the horizon size. So in this limit, the geometry becomes very simple close to the horizon because it simply is given by the tensor product of two spaces, AdS2 and a transverse space, which in 4D would be S2, in 5D would be S3. And the radius of AdS2 and S2 or S3 are related depending on whether or not I'm in AdS or in flat space. So this is just part of my solution. And what I want to do now is consider excitations around the solution. So to do that, I can simply expand my dilaton field chi around a constant value, which represents its value at the horizon. So phi 0 will parameterize the size of the horizon at extremality, plus some excitation phi around it. Now what I can do is plug this expansion into the action, expand in powers of phi, and higher powers of phi will be more suppressed by phi 0. So here phi 0 is a dimensional number that's related to the entropy of the black hole. So if I work in a phi 0 expansion, it's as if I work in a large charge expansion for the black hole. So higher powers of phi are suppressed by phi 0, so I can neglect them. So at linear order, what do we find? We just find phi 0 multiplied by the 2D Ricci scalar, But additionally, and very importantly, in order for my theory to have a consistent variational principle, I have to take into account a Gibbs-Hawking-York term at the boundary of my space-time. This just gives me an integral of k. And very nicely, in 2 dimensions, these two terms add together due to the Gauss-Bonnet theorem to give the Euler characteristic of the manifold. So the sum of these two terms simply gives me 2 pi times phi 0, which in terms of q is just pi q squared. So this is precisely the extremal black hole entropy that just appears in the action just from the leading term in phi 0. Okay. So then I can consider the linear term in phi. So the linear term in phi simply multiplies the Ricci scalar plus some 2D cosmological constant that gives you the radius of AdS2. For instance, in flat space, this radius of AdS2 is set by the charge Q of the black hole. In AdS5, for large, there's small black holes and large black holes. Small black holes are pretty much the same as the black holes in flat space. Large black holes have the radius of AdS2 be the same as the radius of AdS5. In any case, so the point is that this parameter that sets the cosmological constant depends slightly on the parameters of the problem, but the action is always the same. So then, for instance, if I try to integrate phi out, since phi appears linearly at this level, what this does is that it just sets the radius of AdS2 to be constant. So I'm simply describing a patch of AdS2, but its boundary is not completely set. And that's simply because there's a Gibbs-Hawking-York term, once again, just like in the topological term, that is needed in order to have a consistent variational principle. So this Gibbs-Hawking-York term, in some sense, is the only dynamical part of the problem. Since phi acts as a Lagrange multiplier, this term just completely vanishes when I integrate phi out. So the only thing that gives a weight to this Euclidean action is this term, this boundary term, where k is the extrinsic curvature of the boundary. So for a fluctuating boundary, k will have some profile, and I'll get different actions depending on the different shapes of the boundary. Very nicely, if I'm in AdS2, I can try to actually solve for what this k is. So for instance, if I impose that the boundary length is constant, then one can solve for one of the coordinates of AdS2 as a function of the other, and parameterize the boundary by some time, which I'll call intrinsic time, that I'll call du. What appears when I solve for one of the coordinates of AdS2 as a function of the other along this boundary curve is what's called the Spartan Derivatives, which is simply t triple prime divided by t prime minus 3/2 t double prime divided by t prime squared. Okay, so essentially what I've done is I've started with a 4D theory or 5D theory, reduced it to 2 dimensions, noticed that the near horizon region is fairly rigid. The only surviving modes are modes in which the boundary of the near horizon region fluctuates. And the weight of these different curves is just captured by the Schwarzian derivative. So if I try to expand even further, what I obtain is higher and higher powers of phi, but those are suppressed in phi 0. And if I take phi 0 to be my largest, dimensionless parameter in the problem, I can neglect all higher powers of phi. So that's why the near extremal limit is in some sense very simple, because the action reduces to something that's just linear in a non-dynamical scalar field that can be integrated out. The value of the dilaton is constant at the boundary of AdS2. And this is where the energy scale E that I talked about at the beginning of the talk reappears. So one can actually compute what this dilaton is at the boundary of AdS2. It's simply the radius of the transverse space at the boundary of AdS2. And one can check that it's simply given by the scale ESL2 that appeared at the beginning, at which a breakdown of thermodynamics is expected to occur. So in AdS5, this is how the scale ESL2 scales with the radius of AdS, the Planck constant in 5 dimensions, and the charge of the black hole. So this is for the large Brightstone-Nordstrom black holes in AdS5. So now the only thing that remains to be done is to try to understand how I can capture quantum fluctuations of this boundary curve, because those are the only degrees of freedom that could give me something that's not suppressed in phi 0. So before I discuss the actual quantization of that theory, I want to make I want to show you a simplifying step that tells you that the partition function does not depend on beta and on the scale ESL2 independently. So namely, the parametrization of the boundary time was chosen arbitrarily. There is no reason to choose a time u instead of performing a diff and choosing a time a times u. These two times are on equal footing. So rescaling the boundary time u by a times u, it's as if we're rescaling the inverse temperature of the black hole by the same factor of 1 over a. And a simple calculation plugging in this diffeomorphism in the Schwarzian derivative shows you that the coupling in front of the Schwarzian, which is given by the dilaton at the boundary of the AdS2 region, shows you that that also scales like 1 over a. So since our result should be independent of a, since the choice of boundary time is chosen arbitrarily, it means that the end result can only depend not on phi b and beta independently. It can only depend on the ratio of phi b over beta, which is the same as the ratio between the temperature and the energy scale at ESL2. So this is the effective coupling in the theory. And what I mean by that is that one can actually try to solve for that Schwarzian derivative classically. When t is much bigger than ESL2, it means that the coefficient in front of the action, which is phi b over beta, is much larger than 1. So I can just use a saddle point approximation to understand the path integral over this boundary mode. And the path integral is just dominated by the classical configuration. The classical configuration is one in which the extrinsic curvature is constant. And the solution is precisely the Brightstone-Nordstrom solution without any excitations on top of it. So this is the classical limit. But notice this is precisely the limit that we found to be boring. This is the limit in which we expect thermodynamics to be valid, right? T is much larger than ESL2, and the classical answer should be correct. But notice that in the quantum limit, when t is of order ESL2, the coefficient in front of the Schwarzian action is given by phi b over beta, which because t is of order ESL2, phi b over beta is of order 1, which means there's no large parameter in front of the action in this particular case, which means that I cannot simply approximate the path integral over my degree of freedom tau by a saddle point. Instead, I should perform if possible, I should perform the path integral exactly and see how that affects the partition function. And in this limit, all other modes are suppressed by phi 0. So this is the only strongly coupled mode as the temperature is very low. Luckily for us, the path integral over the Schwarzian mode can be computed exactly. So this is the only strongly coupled mode in this entire theory of gravity. The rest can be addressed by classical saddle point. And for the strongly coupled mode, I can do the path integral exactly because of a property called fermionic localization. And that just has to do with the fact that the integration space for the path integral of the Schwarzian mode is slightly special. It's what's called a symplectic space. That's sufficient to conclude that the Schwarzian partition function can be approximated, is not approximated, is exactly given by its classical action corrected by only a one loop correction. In principle, in quantum mechanics or in quantum field theory, one has to compute an arbitrary number of loop corrections as strong coupling. But there are special theories in which one can prove that mathematically the path integral is one loop exact, and this is one example of such a theory. So the partition function of this mode is given by its classical answer. So this is just 1 over ESL2 times beta in the exponent, corrected by a one loop correction. This one loop correction is given by the fact that there's a series of SL2R, there's a series of modes, why one can expand the Schwarzian action in modes, and there's 3 modes that are actually 0 modes. And those are the modes corresponding to the SL2R isometry of AdS2. And for each such mode, if you do the calculation, it turns out that each such mode contributes with a factor of 1 over beta to the 1/2 multiplied by ESL2. So in total, I obtain a 1 over beta to the 3/2. All right. So this is very important, as we'll see in a second, when we put everything together. So let's now take all the results and look at what the partition function of Rice-Nordstrom black holes in the canonical ensemble where we fix Q and beta is. So first, there is a contribution that comes from the action from outside of the near horizon region. That's because we have to consider the space-time up to asymptotic infinity, and we can evaluate the action in between the throat and asymptotic infinity, and we get a very simple contribution, which is just beta times Q. So this is just sets the energy level of the extremal black hole, right? This is just like the vacuum energy in the sector of fixed charge. The second thing is that, as I said, there's a topological term in that 2-dimensional action that just gives me e to the pi q squared. So most people will immediately identify that as what's called the extremal entropy. And this extremal entropy, in fact, gets corrected by logarithmic corrections that go like q to some power. And these logarithmic corrections have been computed by Sen by considering actually the, you could equivalently say that he considered the path integral of the KK modes that existed in that background that we've so far neglected. So those don't give you a change to the temperature dependence of the partition function. They give you an overall multiplicative factor in the partition function. So finally, the answer that I wrote previously for the Schwarzian action here can be written as a density as an integral over some density of states. And this density of states is just given by this function that's a sinh of square root of E divided by ESL2. And this is weighted by a Boltzmann factor, e to the minus beta E. And then on top of that, there's all the higher powers of phi that I've neglected and all the further contributions from KK modes, which give me 1 plus corrections that are suppressed in Q. So this can be seen as the leading answer in a large Q expansion. So importantly, now if I plot what this density of states looks like, you can see that there is no gap. Instead, what happens at the energy scale that goes like 1 over phi r, or ESL2, the energy scale ESL2, is that the density of states is massively affected. And instead of following the curve, which is the semi-classical curve, it deviates a lot because the partition function is corrected by a one loop determinant that goes like 1 over beta to the 3/2. So importantly, what it means is that as the temperature goes to 0, the density of states, or as the energy goes to extremality, the density of states goes to 0, which is precisely the opposite of what people have expected in the past, which was that there's a huge degeneracy at extremality. But since that degeneracy was not explained by any symmetry principle, we maybe shouldn't have expected it to be there. And indeed, a calculation that takes into account the temperature dependence of the one loop determinant shows that that is not the case. Yeah, so this is the answer for large black holes in AdS. What this means is that if I imagine the plot of energy microstates above extremality, the gap does not behave like ESL2, but instead at most behaves like ESL2 times a factor of e to the minus S0. And that we can conclude because we actually have some control over the perturbative corrections and powers of 1 over q in that series that I showed you earlier. And none of those can generate a gap. It's only possible to generate a gap through non-perturbative corrections, and those non-perturbative corrections should go like e to the minus S naught. Good. So instead, the meaning of e to the S naught is not that it's the degeneracy of the ground state. It's that if I measure the total number of black hole states within some energy window between, let's say, the extremal energy and some gap above it, the total number of such black hole states will scale as e to the S naught, but there's not an exact degeneracy. So as a disclaimer, I get asked a lot, this is not an exact counting of microstates or anything like that. Instead, we're only probing the value of a gap and average density of states that we have at low temperatures. It's somewhat similar if, I'm sure some of you have studied the Cardy formula. So it's somewhat similar to that. Now if I want to revisit the old puzzle, yeah.
So what's wrong with this earlier reasoning that people thought there's a...
Yes. So for instance, there's like the computations of Sen that computed quantum corrections to the black hole entropy. And the thing that was slightly wrong with it is that in addition to the modes that he expanded in, there's actually an infinite number of bosonic zero modes at 0 temperature. So in principle, his reasoning is, okay, there's some regularization scheme that gets rid of those bosonic zero modes and gives me a order 1 number. But it turns out that if you turn the temperature on a little bit, those zero modes become precisely the Schwarzian modes that I talked about. So they gain a small mass that instead of being exactly 0, it's proportional to the temperature, T. And putting this theory, putting the black hole at finite temperature gives you a way of regularizing those zero modes rigorously. So instead of getting an order 1 number, the answer is that the contribution of the zero modes is 1 over beta to the 3/2, which goes like t to the 3/2. So when t goes to 0, this tells you that the correct regularization for the zero modes should give you 0 instead of giving you an order 1 number. So that's why the reasoning previously was I guess incomplete, not, I wouldn't say incorrect. So if I want to revisit the old puzzle, in looking at what the energy is for black holes above extremality, I have to take into account this correction to the partition function, this multiplicative correction. And this multiplicative correction appears as a linear correction in T. So instead of the energy going like T squared, I now have a linear correction that goes like 3/2 times T, where the power is just given by the total number of zero modes that I end up with due to the isometry of AdS2. So now one can see that the average energy of the black hole above extremality is always larger than the average energy of one Hawking quanta that the black hole can emit that's linear in T. But of course, like this calculation should be further refined because one might expect that there's some back reaction on the Hawking radiation itself. So it might be possible that the average energy of a Hawking photon no longer is even linear in T. Okay. So a summary of the approach that we've taken is that we didn't necessarily have to do this entire reduction. It's just the most concrete way of computing the partition function, but it's sufficient to actually look at the near horizon isometry, which exists for these solutions close to extremality. So for the Reinstein-Nordstrom black hole, this near horizon isometry was SL2R. And as I turned on temperature, the role of the Schwarzian is that that boundary wiggle slightly broke SL2R in a controlled way by assigning, to each type of wiggle mass that's given by the temperature of the black hole. So then I can find the low temperature dependence of the action of the black hole. That was that factor of 1 over beta in the exponent. And together, by knowing the isometry that's broken, that tells me what zero modes still exist when I integrate over the Schwarzian modes. And these two things determine the log beta corrections to the free energy and can reliably compute the low temperature dependence of the partition function. So this was for Reinstein-Nordstrom black holes. One can in principle do the same for supersymmetric black holes. So for instance, an interesting class of black holes that Chris here has made a great contribution to are the 1/16 BPS black holes in AdS5. These are black holes that actually exist in AdS5 times S5. And they rotate both around S5 and around AdS5. So they're very complicated solutions. Here I wrote the metric. The metric depends on a certain set of functions. The point is that all the functions the parameters of the black holes are just captured by 4 parameters, A, B, Q, and M, the mass of the black hole that appears here. So we can think about them as very generic solutions that have rotations around all axes in 10D and have dependence on 4 parameters. When such black holes preserve some of the supercharges of the theory, at extremality, they're called BPS. The ones that we'll be considering are in type 2b supergravity in AdS5 times S5. So these are dual to heavy states in n=4 super YangMills and have charges delta, which gives the mass of the black hole, J1 and J2, which give the angular momenta around the S free and S5. And R1, R2, R3, which are the angular momenta around S5. S5 has the isometry group SO6 that has free cartons, so it has free angular momenta. It's not like our particles where there's only one angular momentum. Were discovered by Chris and others are 1/16 BPS solution in the sense that they preserve only 1/16 of the supercharges in the theory. Black holes, we can ask again, what is the density of states and whether or not they have an exact degeneracy at extremality, just as we asked before. So we're asking whether or not the calculation that we performed before is changed because now we have supersymmetry. And there's solid reasons to believe that the previous calculation needs to be changed. And that's because on the boundary side, I can compute an observable called the Superconformal Index, which is supposed to count these protected states. So these BPS states are predicted by some supersymmetry. And there's a trick to actually count the number of states in such a theory that are predicted by supersymmetry, and I get a non-zero answer, and that answer is very large in terms of the charges of the black hole, which means that exponentially large, which means that I expect there to be degeneracy. So if I don't find the degeneracy here, it means I probably made a mistake in my previous calculations and everything is off the table. So relatedly, now we want to ask whether indeed the scale ESL2 that appeared previously can now really be identified as a gap in the same way as Maldacena and Susskind or Maldacena and Strominger found the gap in their D1, D5 system. So unfortunately, I don't have a lot of time, but I can just tell you the results for these black holes and contrast them with the non-supersymmetric answers. Let me skip this. The main difference between the black holes that are present in N=4 super YangMills is that they preserve at extremality a different group in their near horizon region. So fluctuations of such black holes are not captured by the Schwarzian, which captures the breaking of SL2R. They're captured by an effective theory that captures the breaking of a more complicated group. In this case, it's a supergroup, and this supergroup is called SU1,1/1, and it's an extension of SL2R. So SL2R is a subgroup of this space, of this superspace. And that's because in the near horizon, I don't have only AdS2 times S2 or S3. I have in the near horizon region, I end up with a space that's given by AdS2 times S3 times S5 that has some fermionic excitations around it that doesn't change the action, since the action is invariant under supersymmetric transformations. Of this SU1,1/1 because that's very simple. So the bosonic sector is simply given by SL2R times U1. SL2R was the group that we talked about that captures the isometry of AdS2. But in addition to that, this SU1,1/1 has an R symmetry, a bosonic R symmetry, which in this case is U1. And this U1 is a certain linear combination of the cartons of S3 and the cartons of S5. So I can again, just like in the case of the Schwarzian, write down some effective theory that appears from the dimensional reduction that captures the breaking of SL2R times U1 times, some fermionic degrees of freedom that are needed to complete it into SU1,1/1. So this is simply given by the Schwarzian theory, coupled to a U1 mode. So here sigma is a compact boson that captures these U1 fluctuations. And both of these degrees of freedom are coupled to some fermionic degrees of freedom that are needed in order for this to capture the breaking of SU1,1/1. And very importantly, due to supersymmetry, it turns out that the coupling of the Schwarzian mode and of this additional U1 mode that captures the R symmetry of the black hole, the two couplings are actually related and equal. And this energy scale that appears not ESL2 or EU1, but ESU1,1/1. Sorry, SU1,1/1, yeah, because that at the end of the day is the energy scale associated that we will associate to the breaking of the supergroup. So one little issue is that in the case of the Schwarzian, we only had to find the overall coupling in the theory. In this case, we have to find two additional parameters. These additional parameters are the radius of the field sigma which is the U1 mode whose breaking we have to capture. So this is like 1 over R, and it turns out that in order for the partition function to be consistent, this 1 over R has to be quantized. And in addition to this, there is a theta angle that's possible for this U1 term. And this theta angle is just given by an integral of du times a total derivative. And this might seem like a trivial term because I can just integrate the total derivative. But since sigma doesn't have to go back to itself on a circle, it can go back to itself plus some integer times 2 pi r. This term might not necessarily vanish. So it's like analogous to the theta angle in QCD, but in 1 dimension. And very interestingly, based on what the value of R is and what the value of theta is and what the value of this energy scale is, my spectrum could be drastically affected. So in some cases, it turns out that there's a gap. And in some cases, it turns out that there's no gap and no degeneracy based on what the value of theta and R is. So the question is, in n equal 4 super YangMills, what situation are we in? What are all these couplings and what do we get? So we can do the calculations exactly. Again, we have to account for the one loop determinant and the classical value of the on-shell action. And the answer that we find here is the action. Here are the contributions of the one loop determinants that we can compute around this background. We can determine these parameters, the thing that we would refer to as the extremal entropy of the black hole as a function of the parameter A, B, Q, and M. S star has this dependence on A and B. R star has this dependence on A and B. ESU1, 1/1 has this dependence on A and B. Importantly, A and B are order 1 numbers. So what you should be looking for here is the dependence with N. This is the dependence with G Newton, essentially. So here N is a large number. So the energy scales that we're trying to discuss are order 1 over N squared. So they're very small energy scales above extremality, but our computations are still sensible at those energy scales. And importantly, in the previous computation, we can now, by evaluating the classical action, we can now actually see what the parameter little r and theta are. And it turns out that for type 2b supergravity, the relevant theory, the relevant effective theory that describes the degrees of freedom near the horizon have the radius of sigma to be 1 and the theta angle to be 0, which leads to the following conclusion, that if I take the answer that I had before that had the one loop determinant and classical action, I Laplace transform that to get the density of states. The answer is the following when, what is the chart? Okay, I'll answer the questions in the chat afterwards. I'm almost done. The energy dependence of the density of states when R is equal to R star. So this is the R charge that for which BPS states exist. Takes the following form. It's an exact delta function at extremality, and that's due to the fermionic one loop corrections, above which there is a gap, and at the gap there is density of states that looks like a continuum. Of course, it can be corrected by non-perturbative corrections to very tiny spacings between black hole microstates. But the important thing is that in contrast to the non-supersymmetric case that we've discussed earlier, the fact that the effective theory changed by a little bit because the near horizon isometry changed from SL2R to SU1, 1/1 means that now I actually can see an actual degeneracy at extremality and a gap above it with a density of states that can be fully determined. It's just given by some complicated combination of trigonometric functions, but it's completely determined. for sectors where the R charge is different than that of the BPS states, there's no delta function, so there's no degeneracy at extremality. There's only a degeneracy when the black hole preserves some supersymmetry. And here I plotted, so these are the density of states in two R charge sectors. Here I plotted in what regions extremal black holes exist and what the classical answer is. So here, R minus R star is how much we're deviating in the R charge sector away from the BPS limit. So the BPS black hole is over here. In the gray region, they're all the non-BPS black holes. We see, well, maybe it's hard to see from back there, but there's the gap here that corresponds to this gap when R is equal to R star in this charge sector. And for all other charge sector, or all other charge sectors, there are black hole states that exist in the gray region. This should be contrasted with the yellow line. The yellow line is the line that the classical action predicts that there are at what energy levels the classical action predicts that there are extremal black holes at. So notice that when R is different than R star, our prediction is that there are black hole microstates that go below the classical extremality bound. And of course, all these black holes obey the BPS constraint, the BPS inequality, which tells you that delta minus delta BPS need to be larger than the difference between R and R star. And it can only be equal when R is equal to R star and everything is equal to 0. And these are the BPS black holes that are located over here. And we've actually computed stringy corrections in these backgrounds as well, and have found that our conclusions are actually very robust in the sense that stringy corrections only affect the coupling of the Schwarzian but through alpha prime corrections, but it doesn't actually affect the temperature dependence of the partition function. So the previous plots hold with stringy corrections, they're just rescaled by alpha prime corrections. So without supersymmetry, so to conclude and summarize, without supersymmetry, there is no gap. The semi-classical analysis that Gibbons and Hawking performed a long time ago shows that the density of states is correctly captured at large energies, but at low energies, quantum corrections become important, and the density of states gets massively corrected to the point where at extremality, the density of states appears to be 0, and there's a complete lack of degeneracy. In the presence of supersymmetry, we see that BPS black holes are special. They correspond to exact delta functions in the density of states. That's an answer that can be obtained by just taking into account all the one loop corrections and summing over the various saddles that contribute to these black holes. And above these BPS states, there is a gap, after which there's a continuum of states.
What is the value of J1 and J2 in this plot?
They're just fixed equal to each other. And well, they're arbitrary in the sense that they determine R star. Like R star depends on J1 and J2. And I fix J1 equal J2 and fix R star to be the correct function that gives you the BPS value of R star.
So this gap has anything to do with like the gap normally people talk about in AdS5 like it's higher spin?
No. That's not the gap that people encounter in these black holes. No, this gap, yeah, it hasn't been discovered before in AdS5. This gap is of order 1/n squared. So it's very tiny from the CFT perspective, because in gravity we take g Newton to infinity, so we take n to infinity, right? So this gap in principle goes to 0 if I consider strictly the n going to infinity limit, but if I consider 1/n corrections, it survives. Okay, and here I have a little table that summarizes the various different cases in which one finds, in which one encounters the super-Schwarzian with various amounts of supersymmetry. The cases that I discussed in this talk are n equals 0, that corresponds to the Reiser-Nordström black hole at fixed charge, where there's no gap. I've also discussed the n equal 2 case, that whose near horizon isometry that's broken, that the super-Schwarzian captures is this SU1,1/1 that's relevant for BPS black holes in AdS5. But whether or not there's a gap depends on the value of R and the theta angle. And there's actually examples in AdS3 that we found that have no gap and no degeneracy. So the answer in n equal 4 super-YangMills was not based on symmetries alone. It was a strong coupling computation. And one can also do computations, for instance, in supergravity and flat space in 4 dimensions. Reiser-Nordström black holes there's a different near horizon isometry that's relevant. And indeed, there one finds that there's a gap as well. That's actually related and precisely the setup that Maldacena and Susskind consider where they found the gap in string theory. Okay, so that being said, sorry, went a bit over time. Thank you very much. Are there any questions?
Could you go back 1 or 2 slides from that, where you have the curve with the,
Yeah, right?
one more onwards.
Yes.
Yes. So the region there is where E is small, right?
Yes.
Yeah.
So it's not, this is E being M minus M naught.
Right.
It's like how excited I am above extremality.
So the modification there is sort of like just subtracting E's the S0 almost. Because
No, well,
if you take that expression, subtract E's the S0, and if you say E is small, then it will give you root E times E's the S0, which is what you have.
Sorry, subtracting.
I mean, if the exponential is expanded because E is small,
Right, you would obtain 1.
you got 1 plus.
Yes.
And then
Okay,
subtract off
I
E's
see what you're
S0.
saying. Yeah. Okay, I'm not sure if that's a coincidence. It's just that it's the function that I'm expanding is sinh. The exact density of states is given by sinh of square root of V, which has an expansion that goes like square root of V at low energies and goes like e to the square root of V at large energies. And I have to say, this result can also be obtained in the particular case of theories dual to 2D CFTs. One can obtain this result without even relying on the Schwarzian theory. It's if one can obtain it as a refinement to the Cardy formula that predicts that at large energies, the density of states goes like e to the square root of delta. I think there was also a question from the online chat. Let me open it. Okay. What is the charge dependence of the partition function and spectrum for the Reiser-Nordström? Thanks, my microphone doesn't work. Okay. So what is the charge dependence? Good. So the charge dependence of the partition function, I actually wrote it a few slides back. Sorry. Yeah, there it is. The density of states as a function of charge is given by e to the S naught with some corrections that go like log S naught. So it's q to some power, e to the pi q squared. So this is a very large number times sinh of square root of e divided by ESL2 of q. And I wrote what ESL2 of q was a few slides ago. So this ESL2 of q as a function of the charge goes like q to the 2/3 for large black holes in AdS5. So that's the charge dependence. Yes.
So you said you're not counting states, but that's, I mean, you
You,
made the disclaimer, but
yes, you're counting, as in what I meant by that is that we're counting states in a statistical average. we're not counting states in the sense that we don't expect that with this calculation, we'll, for instance, see that if I go within an energy interval, let's say between E1 and E2, and count the total number of states living in that interval, I would obtain an exact integer, which is what you would get in string theory through counting of BPS states. So it's a statistical average. One can hope that maybe that's corrected by non-perturbative corrections, so by corrections that are not black hole solutions necessarily, and that by summing up all those corrections, one might obtain an exact integer. If you're interested, there's a specific example that I have in mind that actually achieves that. So, yes.
Oh, sorry. So one lesson I might have gotten from Spartan Derivatives was, they count BPS states, but you might hope that it provides some sort of general procedure that might work analogously for more general theories. Like, is one takeaway from this that perhaps is more suspect that?
Yeah, 100%. Yeah, like I think this computation very concretely shows that non-extremal black holes, don't have degeneracy. So if you ask what is the number of states at extremality, I suspect I cannot prove to that level of detail since there could be non-perturbative corrections, but I suspect that the answer is 1, since there's no symmetry protecting any degeneracy. So we can only prove that it goes to 0 as the energy goes towards extremality.
Great. So, can you comment on like the general program?
Yeah. So in principle, for every theory, so all the theories in which the degeneracy can be counted in string theory that do not rely, there are some papers that rely on simply saying that the degeneracy that exists at weak coupling is also correct at strong coupling without any without any principle of like guaranteeing that. In the Strominger and Vafa case, it is guaranteed because it's a quantity that's protected by supersymmetry. So it's invariant under deformations by marginal couplings. So in all the cases in which supersymmetry guarantees that that the degeneracy is non-zero and that I can count it in the UV, then the type of Schwarzian that captures those situations is either the n=4 super-Schwarzian or n=2 super-Schwarzian, and they all actually have a degeneracy. There's also a case in which the index counts exactly 0 in string theory because there's an exact cancellation between bosonic states and fermionic states. And it turns out that the n=2 super-Schwarzian also knows about that and counts that correctly. Okay. Yeah, so just to summarize, all the cases that people have considered in string theory where there's degeneracy at extremality are captured by these examples because they have supersymmetry. When there's no supersymmetry, we don't think that there's a degeneracy.
Thanks.
Any other questions?
There are some questions in this chat.
Oh. Sorry, let's see. What is the example that correctly counts the states? Did someone catch that? Does Yanis mean the string theory example that correctly counts the states, or the super-Schwarzian example that ends up giving a non-zero degeneracy? Oh, string theory example. Strominger and Vafa in the D1, D5 theory counts, they famously counted the number of BPS states at extremality. Great. Any other questions?
There are no questions.